Hello folks, we're going to do some more differential data flow today. We're not going to do a programming exercise the way we have in the past. What I thought I would do, or I mean we might do a little bit of that, but what I thought I would do instead was talk you through essentially a recent change that landed in differential data flow. And if you just looked at the change, you might wonder why in the world would we do the following things. I thought I'd build up to a little bit about some of the concepts in differential data flow and why the changes that I'll then talk through are potentially interesting. So let me bring this up instead. So in differential data flow, we typically work with these things called collections. And collection, you can sort of see here if you're reading the comments as we go. You don't need to do that though. So this collection type is what's at the heart of differential data flow computations. Each time we interact with a thing that we think of as, the edges in the graph or the rows in some relation, whatnot, we're typically talking about a collection. A collection is just a struct in differential data flow. That struct is really nothing more than a wrapper around a timely data flow stream of triples. And what this stream describes is essentially the continually evolving changes to the collection. So we might say that at the moment we have some, let's say like initially empty collection of graph edges. And over time, over the course of the computation, that set or collection, what could be a multi-set basically, will evolve. Right? So it will change in various ways, may change in various ways, doesn't have to. And this stream describes what are those changes, when do they occur logically, and what do they mean about the new contents of the collection. So this stream, in timely data flow, stream has two generic parameters. There's a data flow graph in which it lives. That's not going to be too exciting. And there is then a stream, the data type, which is triples, basically. The type of the element being streamed around is triples, where the three elements of the triple are, informally, some data. So D here is for data. So this would be the graph edges, a pair of source and destination. Or if you have a relation, maybe the row in the relation that you're thinking of updating potentially. Essentially, it's just the payload associated with the multi-set that we're describing. There's also a timestamp. This is the logical time at which the update is supposed to happen. So these updates don't necessarily happen in the order that they are presented. They can happen in whatever order you like. You just need to write down the actual timestamp there. So if we want to load up 1 million graph edges and have them apply one after the other, we might pick the number 0 up through 1 million as the timestamps. And each of them, even though we deliver that pile of updates at once, the timestamps presented as part of this update tuple will make it clear to the system underneath that this is actually happening at a different time, and that when it reflects on these changes to a collection, then any downstream computation should respect those logical times. And finally, and this is going to be the subject of this explainer, there's this R term for weird reasons. It's called R. It used to be a ring. And a ring is an algebraic structure that actually doesn't really exist in the code anymore, though I haven't really found a better variable to drop in there. We'll see maybe after the end of this talk that G would have been a good one, but G is kind of already taken at the moment. So what R is, most commonly, R is something like signed integers. So R is describing for this data at this time what actually happens, like what change occurs. And most commonly we're talking about a change in the number of occurrences of a record. So maybe this is a +1, maybe it's a -1. If we want to add a record to a collection, we'd have the record, the timestamp, and then a +1. If you want to remove a record, have the record, the timestamp, and a -1. And for various reasons, these +1s and -1s might become plus 57 or minus 14. We don't expect to see a lot of zeros, so we do a pretty good job of making sure that 0 doesn't actually show up as a thing. So you can sort of think of this as a non-zero item here, but it's not something that we actually enforce. But what this is describing, all of these update triples, are the way in which the collection evolves. So great. So integers, plus minus, that's pretty great. It's pretty general. We can, and in fact, we have for quite a while with differential dataflow used integers to great success. When we count the number of records in a collection, that's, for example, for sets, we can absolutely count up all of the occurrences, the multiplicities of each of the records, and for a set, they're going to add up to 1 or 0, because that's true for sets. But integers work great there, and they remove some of the complexity that trying to bind too strongly to sets introduces. Now, that being said, integers are actually way more general than we need. So what I thought we would talk about is what are the actual constraints on this type here, this thing that you normally think of as integers, but we're going to think about relaxing in various ways in the interest of, let's say, performance. So let's take a peek. So the only constraint here is that R implements this thing called semigroup, and semigroup comes from this difference module. So let's hop over there. Now, the change that happened recently was that we made this all a fair bit more general. What used to be the case was there used to be this type diff, and everyone just had to implement diff. And diff essentially is this synonym for abelian. And if you know your abstract algebra, an abelian group is a set of things. So the integers happen to form an abelian group, but it's some collection of values that support a few operations. Let me point out what those happen to be. The exposition, now that I think about it, is a bit backwards because the properties accrete in a direction that we're going to, or that we have already peeled back, essentially. So an abelian type is one that supports addition and effectively negation in place. So you can take two objects, you can add them together, and you get another element in the type. And you can take any one element and say, what's your negative? What's the thing that if I were to add to you would produce an element that is essentially the 0 element, that has the property that if we were to add it to anyone else, we get back whatever we added it to. And the integers are clearly such. The signed integers clearly such a type. Any signed integer we can add two of them together. We get another integer, and we can negate any integer. And when we add it to itself, we get back 0, the integer 0, whose behavior when under addition is really boring and does basically nothing. So that's cool. That was back in the oldie times. We had one trait. It wasn't called abelian. It was just called diff back then. And you had to implement add, and you had to implement neg, basically. At which point we could use you all throughout all of differential data flow, because it's a super general type. The only things we needed to do when we talk about changes to collections were add and occasionally subtract things if we needed to retract previous outputs. Great, and in fact we use this all over the place in differential data flow. Most of the times people use diff types. They are in fact either isize, the default, or some other signed integers. Now this isn't, however, the only thing you might need. You could relax this a little bit, and in particular, you can sort of see from this notation here, you could imagine a smaller type, a smaller trait that doesn't include negation. That instead, something called a monoid. What's a monoid? So monoid is, in some ways, is an abelian group without negation. So in monoid, we creep upwards. And I'm really sorry for all this. Monoid is a semigroup that has a 0 element. We'll get to what a semigroup is, but a semigroup is essentially something that supports addition. So monoid is a thing that supports addition and also has an explicit function that says here's a 0. Here's a thing that if you apply the addition operator, you get back the same element. The 0 is essentially an identity under the addition operator. And absolutely, like it's very natural to define this monoid trait for our various signed integers. We just need to tell people 0 is the actual 0. So for each of these signed integer types, there's a natural 0 element that we can hand back. And this ends up being useful in certain contexts where it's helpful to be able to name a 0 value even if you do not have a concept of negation. You might say, what's going on? And that's a fair enough question. But to get there, let's keep peeling back the layers, and then we'll start working through an example to show you what's interesting, what's going on. So semigroup, this is the lowest layer that we're going to get to here. Semigroup is just a type that supports addition. Now, it's got a few other things over here too because we want to be able to ship it around differential data flow, but essentially it's a thing that, in the language here we're actually going to say that it's something that supports the plus equals operation. So if in particular it supports plus equals with respect to a reference, another element that is a reference to this type. So if you show up, let's say I'm an integer, you show up with a reference to another integer, I should be able to update myself to as if I had added in the value. This is essentially just addition, but we wanted, add assign happens to be a bit more powerful with Rust. It means that we don't, it's a bit esoteric, but addition requires that you create a new output element. And if your elements have memory backing them, for example, this can be sort of annoying. If you want to add A together with B, and they forces you to create a new C, if you were just planning on throwing away A and B anyhow, you might feel a little bit silly allocating some new memory for C, when you could have just updated either A or B in place. So add assign is the operation that lets us update things in place. And we have a few more constraints, just that this thing should have a known size. The data trait says things like, you should implement debug and serialize and some hash traits and just things that let us distribute the data around. And we should be able to clone you. We do have another method here, is 0. And you might say, hold on, I thought you said that the monoid was a semigroup where we had a 0. What is 0 doing here? And you're absolutely right. A semigroup does not have to have a 0. But there's nothing wrong with having a method asking if a particular type is a 0. And it turns out that it's totally acceptable, for example, to have a type that this always returns false. There are no zeros, potentially. But this is an essential method that differential data flow uses to determine if it can throw away updates. So it's very handy to have this method lying around, essentially implemented for all of the difference types that we might consider using. Even if for some of them it only ever evaluates to false. Otherwise, writing the internals for differential data flow would be terrible if we had types that you couldn't even ask the question, is this a 0? We'd essentially have to have totally different implementations of data structures. And plausibly, they could be more efficient because there isn't a little bit of conditional logic now and again if we know that they will never, ever, ever be 0. But that's not how we did things here. So we have 3 different possible types of difference that we could use here. We've got the full abelian group, essentially, a commutative group. We have the monoids, and we have the semigroups, which just don't support negation and don't necessarily have a 0 element. So why are these different things differently interesting? The main reason here is that it is potentially very nice to be able to strip out some of the complexity of integers and counting and such in cases that we know that we don't need it. So what's an example? So imagine that we're doing some nice set-valued computation like reachability in a graph. And maybe I could try to start hacking this up as I start talking. So let's go find some example. I think we could. Let's start with. I'm going to start with Monoid BFS because this is from a blog post a while back about the monoids. We hadn't quite gotten to semigroups yet, but we're going to want some of these concepts. And let me save this out as I suppose semigroup. We're going to do reachability rather than BFS because that's the right thing to demonstrate here. So let's imagine that we wanted to just do a reachability computation. So here's barf. Unfortunately, the example is pre-complexified for you. You're in luck. So let's imagine we're just writing this without any of this weird notation. And we wanted to take some set of edges, some sets of roots. So the collections here are collections of edge as the data type. The collections here have a single node, and we probably want to start from the roots and then iterate. Where each time around the inner body of the iterative computation, we will want to join whatever nodes are currently reachable with the set of edges. So we're going to let edges equal so we're going to bring the edges into scope here, and we will take the edges. We're going to semi-join them with, semi-joins are unrelated to semigroups. There's no relation that I'm aware of. Probably actually related some important way, but we're going to semi-join these with inner. So what this is we're going to keep pairs source, dest if source is inner. This is what a semi-join does. Essentially it's a join that doesn't bring any data in from the other relation, and it just restricts down edges appropriately. And having done that, we're gonna then say, ooh, dest is probably reachable then. So let's peel out from source, dest. Dest. We will want to concatenate in inner, though actually, let's do it slightly differently. Let's concatenate in roots. So we'll need to bring in roots here as well. So, delete all this nonsense. Oops. So we've defined a computation here. We'll see if it compiles in just a moment. It won't until I do that at the very least. That starts from a set of roots, and then repeatedly we bring in some things and some constants into scope, but repeatedly we take our set of edges and restrict it by the current set, the inner variable that is developing the, we could call this something else possibly, like reached or something like that. But it's a set of nodes that grows with time, that are the nodes that are transitively reachable from anything in these set roots. Initially it's empty. After the first round we concatenate in the roots, we go back around again. There'll be more elements in inner, and that means that we might be able to produce more destination edges, nodes rather. Concatenate roots back in again, go back around again, and the set should just grow. So let's check that out. I'm going to have to see if I can decomplexify this stuff here as well. Reach, great. I'm going to comment this stuff out, though I don't actually really want to delete it just yet. Let's see what happens if I start to what we call a semigroup. There'll almost certainly be some sort of issues. I hope. I mean, typically there are issues, so I'd like them to show up. So that yeah, there we go. Good. All right, it expected a collection, but fine. Okay, so we should not have put a semicolon at the end of that. Tidy up some of these character terms here too. All right. Okay. Good. This example was showing off a monoid, which is exciting, but we're actually not going to use it right yet. So let's see if that successfully evaded that problem. 90. There it is. Oh, up here, right. All right. So we're good to go. So what does the program do? We've written. There's a general program. We're gonna relax it a little bit. It takes in some nodes, some edges. Wait, what's that? Don't worry about it. A batch size, some number of rounds to do, and argument that says should we bother to look at the output or not. And then we build up a timely dataflow computation. We grab we don't need this anymore. We have the worker has its own timer, so definitely don't need that. What we can do, I suppose, is then we're going to define a new data flow, reachability data flow, and we're going to return, as the comment says, we're going to return handles to the roots and edges inputs so that we can play with them. We can change the collection if we want. And all that we're going to do inside here is define some new collections. These are the handle, so the thing that our program gets to interact with, our imperative code outside of the data flow, and then data flow objects that we can then use to build up data flow graphs. These are collections, as we just talked about. The reachability computation gets invoked, and the result is, if we check out the type, the result is a collection of nodes, everything transitively reachable along edges, starting from roots. And then we take that, we count the result, and no idea why we're going to do that. I guess this maybe made more sense in a slightly different computation because we have no interest in counting this. They're going to be distinct elements coming out, so like the count is probably super boring. So let's instead just consolidate the result. And consolidate will has the property that it takes all of the diffs that might spill out there and says, before I show them to you, before I let them pass through the consolidate operator, I'll make sure that there's at most one update for each data at each time. So it takes lots of pluses and minuses or whatever, and then puts them all together before showing it to anyone. Sweet. All right. So that's what's that. And then the program just starts going by putting in this case, we're just going to put in the value, the root 0, and close out roots. We'll make sure we understand that we've pulled the arguments out correctly, so it's a good thing to test. And then worker 0 just sort of runs through and updates the graph a bunch of times. This is to load up the data initially. So we're just going to start with a random number generator picking out random random source and destination edges, the default time, which will be 0, and then a 1. So this is us adding that edge into the graph. Great. That'll be loaded. We'll then start, grinding through, essentially doing our initial computation. So roots already has some data in it. We've now put a bunch of edges in, and this will run until we actually have the correct answer, and we should actually see a result before we see stable with a timer. And then repeatedly, we're going to go through and we're going to, looks like we're just going to create some more random edges, add them into the graph. In principle, at the moment, we could also have subtracted some edges out too, but we should probably have checked to make sure that they actually existed before we subtract them. And then we report some numbers about throughputs. I actually don't even know what those are, but maybe we can find out if we run them. Cargo, okay, great. So let's do this. I don't know, we're going to do something not too exciting to start. Let's do 1,000 nodes and 10,000 edges. We've got to fill in some more arguments here, just to make sure. Weights, no one really cares about. Batch, I don't know what these are. So the batch is how many updates to do at a time. We could do just 1 if we wanted, but 10 might be interesting. And then we inspect things by typing inspect. All right, this will take a little bit of time to build and then run. So so what we're testing with the example is a computation that determines the reachable set of nodes under some modifications to the input data. And at the moment, these modifications use integer difference types. And that's cool because it's pretty flexible for us in terms of the ways that we can modify the graph. We can add edges, we can remove edges. Super neat. But nothing's fundamentally wrong with this. But we can potentially go a bit faster, let's say, or we can communicate something else about our computation if we use a type that is less powerful than the integers. And you might say, what's an example of that? So the type that we're going to consider next is a type that basically just says, I'm present. Oh, wow. Sorry, there's serious typos here to fix. Where did that come from? Oh, I see. I must have... So we could use the integers. Using integers is fine, and we will everywhere keep track of counts of changes of things. In a world where we might have less expansive ambitions, maybe we're just thinking that we're going to do, for example, a batch computation once. Not really going to change anything. Things aren't going to... Things in a reachability computation, for example, are only going to get added. Right? We start with some edges that we add in. We start with a root set into which we add some nodes, and then this reachable set only ever has things added to it. So maybe the only sorts of changes we need to think about are the additions of elements. In which case, we don't actually need to keep track of the numbers of these additions. Right? We just need to have you can think of it, if you want, as a bool that says present or absent. And as of maybe a month ago, that would have been what you would have had to have done. So you would have had to have present, maybe could have been true, and absent could have been false, and addition would just be logical OR, right? So if we have two things and we logically OR them together, then if either one of them is present, then the result is, present. Great. We have false is our 0 element. That's pretty handy. And nothing's deeply, deeply wrong with this approach. However, it is... Ooh! Something exploded. let's see if we can figure out what... So this looks like probably our inspect logic that's printing out these tuples. Yeah, okay, so what we forgot to do, probably a few things, because the crash, this isn't a thing that results in a crash. But what we didn't do was delete the data here. So we're actually seeing all of the nodes that can be reached. And what we might do instead is just say, don't care. Don't care at all. Now, and what this should report instead of the numbers, every node identifier that we can reach listed out explicitly, it should hopefully just tell us the count instead. Now, we have an exciting panic here. I should try to figure out what this is. So this is a complaint that essentially that we've tried to go backwards in time. And that is indeed a bad thing to do. Though, well, let's start this building again. So so this is the sort of thing that happens when we advance graph to 1, and if ever we tried to use graph at 0, there'd be a bit of a problem. Fascinating. I don't see it. I mean, here we go up to 2, and then from this point on, as rounds increase, sorry, yeah, as the rounds increase. Okay, sorry, we have these two calls in here. Great. Okay. Update at update at doesn't produce that sort of error. Just advance 2 produce the problem, but we can. So this should tell us now about each of our attempts to, and let's kill this off and do a nice debug build instead. I'm a little surprised because I'm a little weirded out by the idea that there's like checked-in code that crashes if you just run it. And I don't think we changed anything that should have changed how well it ran. This will go to advancing from 1 to 2. Assertion failed self-time must equal I'm not too bothered by that assertion actually, but let's see what this is. I can't tell, sorry, if this is timeless input or let's check it out real quick. 261. That was filthy. Apparently I should write print one, not print. Advancing, assert 1v1. This looks like the last one that we're seeing there, but maybe that's wrong. So update that does actually complain. Assert 2v1. So we've advanced to 2 and are still trying to insert at. Yeah, this is definitely all sorts of wrong. Who would write such code? I'm really surprised actually that got this far into it. So this should be 2 plus round plus element, I believe. One plus round. Sorry. The way this is set up, we're advancing at the end to the next bit of time. So this should be coming in for 0, 0, should be 1. That's great, that's what we advanced to before. We'll advance to well, sorry. Yeah, the advancing happens here, so we'll advance to 2. We'll back around again, element will be incremented by 1. So you can think of this instead as 1 plus round times batch plus element plus 1. Just save the file. Probably going to want to delete these printfs if we solve the problem. So nothing wrong in differential data flow, just something wrong in the example, which is the pity that I'll have to fix, but I'm good that we got to see this to be able to debug. Oh, look, there it goes. Great. Okay. So this runs, and we can stop printing out lots of spammy text there, and we can go and make this be a more performant build. And this will take a little while, and I'll get some water. So just to talk through the plan, I suppose, what we're going to see here is this will take some amount of time to run. I don't know, we'll try to fixate on, maybe make it a little bit bigger, but fixate on some parameters and try to tease out some numbers that we can look at as we change the code. But the idea is that we're going to try to slot in something other than integers here. We might slot in a bool, like this present absent bool. What we're actually going to slot in is the empty tuple, which the empty tuple is just, think of it as just an announcement saying present. That's all it says. There's no absent. So absent is, it's kind of like the 0 actually. So we don't bother talking about things that are absent from the collection. We only talk about the things that are present, and your presence is sufficient enough for us to realize that you're present. We don't need a complicated integer describing how many times you're present. We just need to remember, yeah, you're here. All right. So this cranked through a whole bunch of stuff. Let's we can now rerun it a bunch of times because so let's take it up to maybe 1 million, 10 million. No idea what this will do. Dial this down a little bit there. All right. So, yeah, let's see. I mean, we could definitely, for example, track how long does it take to reach the stable configuration here. And in principle, we could also look at how long does it take to do these updates. So let's make the updates themselves a bit bigger. I'm just trying to tease out something that has some non-trivial magnitude to it, so that we can see if we move the needle at all. Yeah, so this is good. Or we have some hundreds of milliseconds of stuff, and we can watch these and potentially get faster. An interesting thing, we have added enough edges now that someone who wasn't reachable before, just about everyone, you can see, just about everyone was reachable initially. But we did manage to find at round, an element that we added, 8,223, which I guess is round 8 of patches of 1,000, or maybe around 9. Became reachable, hooray! The count went up by 1. So that's exciting. Maybe we should dial down the number of edges a little bit so that we're not. Ooh-wee. All right, that was maybe too much dialing down. Or at least I just don't want to be spammed by all of the outputs here. We want to be able to see. I suppose we can just turn inspect off. Sorry, I should have just done that. Let's turn inspect off. We can see though that we're producing, various. We have to put something, otherwise it crashes. Great. All right. Well, that looks fun. All right. So now we're taking 4.2 seconds to load up. Let's see how stable this is. 4.2 seconds to load up, and 4.7 something to finish. So about half a second, a little less worth of work. Once we've gotten up and running, and about 4.5 seconds, 4.2 seconds to get us there. Let's stash this somewhere just so that we can refer back to it. Great. So what the heck was I talking about with respect to these empty tuples and stuff? What we're going to do is we're going to create a new type, a bit like an integer. That this example is back when we were doing breadth first search using monoids, but we're going to just do a similar sort of thing here where we just say present. That's the whole struct. There's nothing in it. It has size 0, which is super handy, and it is going to implement a few traits for us. So we're going to be able to add it to itself. You might say, what does that even mean? And the answer is, if I have a present and I add it to a present, you just get a new present, right? This is essentially saying if I want to OR together true and true, what do I get? I get true. But there isn't even a false to talk about here. So these, some of these bits of code look really quite simple, but we do need to tell Rust, what do I do when someone says plus equals? And we could have it panic instead if we wanted, or we could have it. I mean, there really aren't a lot of choices actually. There's not too much that you can do to this type. It doesn't really support a lot of mutation because it doesn't really have any alternatives. And we're going to make sure that it can be multiplied by itself, and that's a bit crazy. And I haven't told you why you want that, but you do want that. When we join things together, the generalization of a relational join is going to multiply together. So if I have 5 copies of a thing in one relation and 4 in another, when I join them together, I get 20 copies, right? Because all of the pairs match. We need to define the same logic here. What happens when I have a present in one and a present in the other, and I join the two together? Well, we know that just means that it's present. But we have to write the code anyhow because that's how programming works. When we say that we implement a thing, we have to provide the code that does it. So this is, I think, roughly what we want. And now what we're going to try to do is each of those places that we did an update at, we're just going to put in present. 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 Great. What does this do? This essentially just strips out an integer from all of these updates that we're working with, and it strips out integers from the intermediate representations of all of the state that we maintain in the course of doing this reachability computation. And that's sort of handy. That just means that we're sitting on a fair bit less data. It has the potential also, though, and this is sort of cool, to do some optimization inside the core of differential data flow. So inside the core of differential data flow, for example, we have for loops that say iterate through all of the differences and accumulate all of the using addition, using all of the what would have been integers, using addition all over the place. But Rust and LLVM are going to be smart enough and look at this and say, nothing actually happens when you call add assign. That's a no-op. So, like all of those loops, we just get rid of those, right? Like those don't even need to be loops anymore. Those can just be nothings, basically. And that's sort of cool. So a bunch of the compiled code internally has the potential to get simpler. So we have a reduction in some memory footprint and a reduction in computation as well. Let's see. Ooh. So add assign. Oh yeah, sorry. Add assign should not return a thing. In fact, add assign should not do anything. Now we right, because we're just saying how should we update ourselves? Yeah, don't do anything. When we called new collection, we need to be more clear about the type that we're planning on using. So Rust says, like, I was pretty sure you wanted to use iSize, and we need to tell it at various moments, no, we're not going to use iSize, actually. So if you want to use something other than the default type parameter, you have to actually specify it. No method named iterate. Oh, right. Okay, so this is the fun stuff now. So iteration in differential data flow is like the concept is still sane, and we're still going to use the concept of iteration. But the method iterate needs to be general enough to understand what happens if your collection after one iteration is fundamentally different from the collection at the beginning of the iteration. For example, it needs to be able to understand how to subtract things. The only logic that it knows is that if you start at x and you produce f of x, then the changes are f of x minus x. So if we have something, for example, that was present in inner and then not present at the end of the iterative computation, or is it of one step, iterate's going to get really confused. Like it needs to have access to, as far as this is concerned, a negation method, because it can't operate without one of those. So, so there's a fix to this, and the fix happily lives over in that there's a bunch of code that we deleted. So we're just going to pop it back open again and look at it. So it's this code here, and we'll sort of talk through what's going on while we're here. Actually, let me steal this stuff and fix that horrible buggy code. Great. So instead of using built-in iteration like we do here, we're going to write something that's a bit more wordy, basically a bit less clear, probably. We're going to hand roll one of these things ourselves using differential data flow's variables. And variables are a way to build up an arbitrary iterative computation with potentially multiple variables that develop independently. But we have to do it ourselves because the cute things like iterate's ability to just subtract the input from the output in order to determine what happened in one round doesn't apply here. So we're going to build our own iterative scope. And apparently we're going to use U32s for our iteration variable, like the counter for rounds of iteration. And then we have a few bits of crazy thing going on here. And this is because we're essentially pulling back the curtains a little bit and looking inside. So we're going to create a variable. And a variable is a thing, a collection. You can think of it as a collection that is initially, whatever it is. We can use it in our computation, and at the end of our iterative scope, we have to bind it to a thing. So we get to produce a definition for the variable, possibly in terms of itself. And it all works out nicely so that if you do use it in terms of itself, it will result in an iterative computation. And if you don't use, if there is no cyclic dependencies, everything all just gets sorted out essentially in one iteration. We're going to need the core reduce operator. So whereas we previously had just said distinct, we're going to kind of need to write this ourselves. And the reason being that I think maybe we might actually be able to use distinct now that I think about it. We'll have to try. We'll see what distinct's requirements are. Distinct might actually let us just use a semigroup, because distinct knows that it doesn't really need to subtract necessarily. But we'll see what we're permitted to do. And we have to name a few fairly explicit types as we go along. So let's just import this, and we will comment this out for the moment, but we will attempt to respect its intent. So we've got our roots, we've got our iterative scope. We should be careful because this is not the default type. Let's make this usize because we want to be able to compare across different numbers. This usize is the type that gets used by iterate, and we want to make sure that we keep as many things fair and fixed as possible. So we've got some imports that we have here. We need to create our new variable. When you create a variable, you name a scope that it exists in, and you describe a promise for how it will advance. So one round to the next, something needs to happen to the times, and we're promising that they will advance by 1. This is essentially timely data flow being very particular and saying, you don't just get to run and see what happens. You have to make structural promises so that we can analyze the data flow. All right, we bring in our roots and our edges just like we did before. We are going to take our I'm just going to look below and sort of try to just rewrite this. We're going to take our edges and do our semi-join. I think we can still do this with our variable. We will do our, I'm just going to peek up here. We'll do our map also. We'll do our concat. So at the moment, we're still doing fairly vanilla-looking things. It's the next operation that's the scary one. Variable. No, I'm sorry, not variable. Roots. Both would work, but roots is better. And now we're going to try to do distinct. And let's try to write it this way. So why is this so complicated? Previously, when we had written an operator like reduce, great, I'm going to delete this so we're not distracted by it. Previously, when we wrote a reduce operator, something like map reduce, that reduce. So we get, for each key, a bunch of input values, and we want to produce a bunch of output values. And there's some fairly natural logic there that says, that we can do behind the scenes that says, well, previously, we're going to keep track of what you produced previously. And previously, you might have produced, I don't know, some totally unrelated set of output values. This time, you produced a different one. The changes, we're going to basically have to subtract the two of them. We're going to have to go and retract everything that you put out previously and output the new outputs. And maybe a bunch of those will cancel. But maybe not, and maybe there's actual negation to go on there. And that's awkward because we don't have negation at the moment. And so that operator, that implementation of reduce, can't really be written against the semigroup type. It can be written against the Boolean type, but we don't have one of those. We've got something else instead. So deeper down in the bowels of differential data flow, there's a method called reduce core. Sort of is the core reduce function here. And what it asks, instead of, with a normal reduce method, instead of showing you, here's your key, here's your input, and please tell me about your outputs, it says something else, which is here's your key, here's your input. Here are the outputs that are going to happen if you don't produce any updates. So please put any updates you might happen to want to put into this buffer. And this should be pretty simple, actually, in as far as we're doing it, trying to do a distinct operator, and there's really not a lot of values to look at. The only thing we need to really check is if output is empty, we should push something into the output. We have to do a little bit of a tap dance here because do a little bit of tap dance because reduce only works on key value pairs, and we just had a set of nodes. But if we see anything in the input, like the fact that we get called at all is an indication that some input is present. And the only time we actually need to do anything is if there's nothing in the output. We should push some updates there. If there's already something in the output, the only thing that it could be is the empty tuple and the present update. So let's see if this actually works. Oops, let me save it. I'll save the monoid one also so that we don't forget. Need a semicolon, like you do. Alright. Mismatched types. Why is that? Expected eye size found present. Oh. So, it's a bug. Alright. So, while this is compiling, let's go check out and actually see what requirements distinct has. I'm sort of curious, maybe we could have gotten away with. So, for example, so distinct lives as a little helper thing underneath the threshold trait. Threshold more or less says that it will put all of your updates together, and then you can apply a function that looks at the accumulated count and produces some result. And threshold does not require the trait itself. It requires that the input type be a semigroup, but it does not obviously. Oh, I see. Okay, so distinct is problematic because distinct only understands the concept of eye size output collections. So okay, so distinct would not have worked as written because as soon as we get this stuff in our system, we're sort of screwed. Now, maybe we could write distinct in a more pleasant way, but for the moment, we essentially hand-rolled it ourselves with this reduce operator. And we're getting lots of warnings here. Absolutely correctly, our add a sign and multiply operations do not appear to use the other argument. It's absolutely correct. Rust wants to make sure that's in what we intended, but really it's the only thing that could have happened. All right. So that went a little bit faster, not exceptionally so. Yeah, great. Okay. So on a nice clean run, just to remind you where we were. we were spending 4.2 mumble seconds loading things up, and now we're doing 4.08 loading things up. And from that point forward, it looks like maybe actually we're spending about the same amount of time in our updates, because it's about half a second from here to here, a little less, and a little less than half a second from here to here. That might make some sense in that the updates are more compute intensive than the initial sort of volume of data manipulation. So this is the sort of thing that you can do with the semigroups. I don't want to get you too excited about the performance benefits here, because as you can see, they're nominal. What is sort of cool is that the memory footprint is kind of substantially reduced. Maybe with a bigger volume of edge updates, we could stress the system a fair bit more. But the thing that I actually think is really cool about this is, having written our program this way, where we have the present type here, we've communicated outwards to people who want to use this computation that the only way that they're allowed to change the data is through the addition of tuples. So we've actually not just put an optimization into place, but communicated upwards that this is a different way of interacting with the data. That this does not support arbitrary changes to the computation. And rather than sort of assuming that or like putting it in the documentation, we actually use types to communicate that you do not get to arbitrarily manipulate this data, you get to interact with it in a much more restricted fashion. And I think that's kind of cool, actually. Or at least I like the idea that the different modes of interaction can be encoded using types. It's sort of cool that you get some performance benefit out of it as well. But no, but I definitely like the fact that we're saying more about our computation using these types. And yeah, sort of curious to start going through here and seeing if there's anything else to tidy up. But these things almost certainly get better if you start changing these to like U32s and such. But we do not need to do that. Yeah, all right. So that's what's going on with semigroups and monoids. Monoids are a little less common now that we have semigroups in place. Not so much that the code actually needs the zero. A lot of the code was rewritten in the semigroup PR to make sure that we only actually use zero in places that we really need it. And there aren't that many places that we really need it. In fact, I don't think there are any. So by and large, semigroups and abelian groups are the two types of things that get used. This is why I thought that maybe G would be better than R, because both of these are types of group. And that at least would communicate a thing, but G is also pretty popular for graph. So that sucks. But yeah, I think we'll stop there for now. I didn't really have much more to say than this, and to try to talk through what's doing in differential data flow. And possibly, if it comes out, this might be useful in some data log evaluation that we're about to do. A lot of the folks doing data log computation have settings where they want to do a data log computation but don't actually need to do incremental updates. And as a consequence, we shouldn't bother to do anything other than just keep track of which facts are present. Not even which ones are absent, because we don't keep track of those. And we'll see, maybe, if I write the code correctly, the difference between semigroup and non-semigroup based data log evaluation in differential data flow when we compare and contrast against these recently published works. But yeah, let's. So we're gonna stop there, and I'll talk to you later.